did the math with Earth's radius, and it seemed to suggest that we would become a black hole if we compressed everything on Earth and all of us into something about the size of a pea.
It's about, from memory, about 0.8 centimeters, I think, something like that, just less than a centimeter. So you're right about that big.
Do black holes that small exist?
No, we don't think so. So even black holes the mass of the sun, the sun will not form a black hole. When it runs out of nuclear fuel, it will collapse, and there's something that can stop it collapsing.
The force of electrons.
It's called a white dwarf star. It's a beautiful calculation, by the way, Dan. You can do the calculation, it's great. So what stops it, as an aside, is that as electrons, there's something called a Pauli exclusion principle.
I read about this, yeah.
So electrons don't want to be close together, roughly speaking, you can say it like that. So as you squash the thing, the electrons get closer together, and so they kind of separate away from each other and go into smaller and smaller little regions of space because they're trying to stay away from each other. But there's also something called the uncertainty principle, Heisenberg's uncertainty principle. So as you confine them into smaller regions, they start jiggling around faster and faster. And ultimately you can reach a limit where they're essentially trying to jiggle at the speed of light, and they can't. And so there's a limit to how much pressure that process can exert. And it turns out it's 1.4 times the mass of the sun, which is called the Chandrasekhar limit. So you can do that calculation, but it's a beautiful calculation because you could have worked that out not knowing that stars exist. All you need to know about is quantum mechanics and relativity, and you can make the calculation, what is the biggest lump of stuff that can be held up by this jiggling of electrons? It turns out it's 1.4 times the mass of the sun. Then you look into the sky and you see there are these things called white dwarfs, these collapsed stars, which are, and there's none more massive than 1.4 times the mass of the sun. So it's very beautiful. And then you can get neutron stars, which are held up by the jiggling neutrons. But ultimately, if you go to something that's three times the mass of the sun, something like that, a bit more, then nothing stops it collapsing. And that's when you form a black hole. So the lightest black holes that we know of are around that mass, right? And then we know of them that are 10, 20, 30 times the mass of the sun from collapsed stars. And then these things, which are millions of times or even more the mass of the sun, which are the heart of galaxies.
So we've launched in our spaceship. We are hurtling toward this black hole.
Yep.
Could you walk us through step by step what happens from now until when we hit the event horizon?
Yeah, so the first thing to say is that it's right at the heart of Einstein's theory is something called the equivalence principle, which was the idea that really led Einstein to the theory itself of gravity. And so you don't feel its pull. What you do is you just fall freely towards it. So we're falling towards this thing now, and we turn our rocket motors off. We can't tell. If we can't look outside, we can't look out the windows. We're just in free fall. We're just floating. So it's like the astronauts on the International Space Station. We're just there. So it's fundamental to Einstein's theory. It's very important, actually, for the problems that follow that we're going to talk about, that you just freely fall towards this thing. So we could be approaching this in this room now, and we would have no clue that that's what's happening. And in fact, so we're approaching the event horizon of a very big black hole like this. For a black hole of this mass, then we wouldn't even notice something, according to Einstein's theory, as we fall across the horizon into the interior of the black hole. So we'd fall across the horizon. From our perspective in this room, according to Einstein, and we'll go for that caveat a bit later, but according to Einstein, into the interior of the black hole we go, and we notice nothing.
What about when we're in the accretion disk? Wouldn't we be
banged
around by a lot of stuff?
So we might get in a bit of a mess as we go through the accretion disk, but we're talking about the pure gravitational thing.
Yes.
You're absolutely right. It's a bit nasty around these things. So there's stuff, but that's nothing to do with the black hole itself, right? It's nothing to do with the fundamental physics. It's all the X-rays and all this nasty gamma, all the stuff that's been irradiated from all this hot material around it. So yes, that would be a problem. But if we had let's say that our room, this spacecraft, is magically insulated from radiation and heat and all those things, then nothing. we would go into the interior. The caveat,
Please.
there's a lot of caveats, but one thing I should say is that it matters that description I've given, it's for a supermassive black hole.
Yeah.
If this was a smaller black hole, so smaller, less massive, a few times the mass of the sun, then at some point you experience what's called tidal gravity, tidal forces. So those are things that raise the tides in the oceans of the Earth. The tidal forces, we will start to, in our freely falling trajectory towards the black hole, at some point you start to feel the tides. You start to get stretched and squashed, and
You feel it.
You'll feel it eventually. You'll really feel it eventually, because formally, as you get very close to the singularity, you get infinitely stretched and squashed. So you really feel it.
I want to talk about that inside.
Spaghettification.
Yes, that's my favorite.
But so for a smaller black hole, as you approach the horizon, you'll feel those forces. But for the big ones, you don't feel the tides until you've gone into the interior.
So we're moving toward the event horizon. We're somehow insulated from the messiness of the accretion disk. We're moving toward it. I've heard that there's a moment where the physics of this are such that if you and I are actually falling in, if we look to the left and the right, we would actually see the back of our own heads.
Yeah.
Is that anywhere close to correct? And can you tell me about the other little details as we approach the event horizon that you think are important?
Well, one of the biggest details, it's not even a detail, it's one of the most shocking things about this, is I've described us falling to the black hole. And we're saying, in this room where we can't see out, what do we feel, what can we measure? And the answer is you can't measure anything and you don't feel anything until we get inside and we approach the singularity for this one. But from the point of view of someone outside, the description is very different. So what would they see happening to us as we fall towards this thing? So even in Einstein's theory, nothing else, no quantum mechanics or anything, then what they would see is time tick more slowly for us.
Mm-hmm.
So they would start to see, as we approach the black hole, if they could see our watches, if we were transmitting to them or whatever it is, transmitting from these cameras we were sending it out to them, they would see our time tick more slowly, more slowly, more slowly, and they would see our time stop on the horizon. So they would never see us fall in. So from the point of view of someone outside, nothing goes into the black hole, ever.
So what, do they see us imprinted there forever, or does the light from us slowly fade until...
It would fade because also you could picture, there are many ways of picturing it, but you could say this light is climbing away from through this gravitational field, so it's getting stretched, so we get redder and redder and redder, redshifted, infinitely redshifted. Time passes more and more slowly until it stops on the horizon when viewed from the outside. From our perspective, we look at our watches, they go at 1 second per second. And that's absolutely central. There's nothing weird, well, there's something weird there, but there isn't according to Einstein. So it's pure Einstein's theory. So that's the first thing to say, and it's a clue to the interesting things about what we're going to talk about. What follows is that there are different perspectives on what's happening here. There's a perspective from our point of view, we're going in for a big black hole. From the point of view of someone outside, we never go in. And that's going to be kind of important for what follows. But there's nothing that's not described by Einstein's theory in that particular bit of the description.
Let me show you something else that's really cool. This is my privacy dashboard. It shows how many data brokers I've gotten myself removed from. Actually, our sponsor, Incogni, has gotten me removed from. So why does this matter? Well, data brokers make money buying and selling your information. Sometimes they sell to businesses, so maybe I get more spam. But also, with more data, these brokers can form a picture of you, a shadow profile, which they can then use in ways you might not want. But Incogni can force many of them to remove you. Let me show you. So they reach out to data brokers on my behalf and they say, hey, remove this person. And then, crucially, they follow up to make sure that I actually got removed. I really appreciate this, and I think you might too. If you want to try it out, use the code CleoAbram at the link below and get 60% off an annual plan. Now, back to black holes. So at this moment, we cross the event horizon.
Yeah.
And we don't feel that
We could have crossed it now,
just now.
wouldn't notice.
And our experience now is completely inside the blackness of the black hole from an outsider's perspective.
Yeah.
Gravity is increasing faster and faster. And this is where we get to maybe my favorite word that I have learned in the process of this, which is my understanding of this is when the gravity at your feet is so different from the gravity at your head that you begin to stretch in a very dramatic way. And this is spaghettification.
Yeah.
Could you explain what is happening here?
Yeah. And
as we
you
get
said,
spaghettified.
one way of thinking about it is that another way of thinking about it is just that the distortion in space-time is not constant over the length of your body. Right? So when we're falling in, we might as well be, this is the Einstein's equivalence principle in action, we might as well be in flat space because the distortion, it's like saying on the surface of the Earth, if you look at a square mile of the surface of the Earth, you don't see the curvature, right? You have to go to bigger distances to see that you're on a curved surface. It's kind of like that. So the distortion, the difference in gravitational pull, as you said, or the distortion, you don't feel it until it becomes very distorted, or there's a big gravitational pull when you get very close to this thing. And then you start to see that, and actually it works. It's not only stretching, it's also a squashing. So the way the tidal gravity works is to squash in one direction and pull in the other direction.
So we are getting...
So you feel it. So you start to feel this strange sort of sensation of being stretched and squashed. and as you go closer and closer to the singularity, those effects become much more extreme, until they're so extreme that first of all you cease to stay together.
We're one long string of atoms?
Yeah,
well, what are we now?
And then the atoms get separated, and then the protons, the quarks inside the protons will get separated, and ultimately, according to Einstein's theory, the tidal forces become infinite. So that formally infinite. And so everything is gone. Everything's been ripped apart. And this is what we call the singularity. So the whole thing kind of gets very extreme and breaks down ultimately in Einstein's picture.
The question that when I began this story I wanted to ask you is, what is at the center of a black hole? But in doing this research, I now understand that talking about the center is also a little bit incorrect.
Yeah.
How should I actually think about what is happening at that singularity?
Well, I mean, the first thing to say is we don't know. Right? So we can talk about the current research and speculation. We don't really have the tools to describe it. So a way to think about Einstein's theory is that, as I mentioned earlier, it really tells you how space and time are distorted. They also kind of get mixed, get up from the point of view of someone outside. So then you'll see that space and time are getting warped and distorted. And as I mentioned, they get so mixed up that on the horizon you see that they flip. So the thing to bear in mind for all that follows with Einstein's theory is this very central idea that if you're freely falling through space, or over space-time if you like, then you don't, in the absence of these tidal effects, you really cannot tell that you're where you are in the universe. If you're close to a black hole, close to a big star, orbiting around a galaxy, just falling, whatever it is. So I think that's the key idea of the so-called equivalence principle. But of course, as we said before, the thing about a black hole is that why don't you see that? You could say, why don't I see these effects on the Earth? This distortion, this mixing, and you do. So you see it in GPS satellites, for example. So if you think about what I said as you go closer to this thing, then as viewed from the outside, time passes more slowly. So you could say, well, why doesn't the Earth do that? And it does. So what you see is that time ticks at a different rate, by which I mean clocks tick at a different rate, atomic clocks or biological clocks. So you age at a different rate in orbit than you do on the surface of the Earth. And you'll see this is the same effect. The reason it gets very extreme, I should say, it's quite a big effect for even near the Earth. So the drift is tens of thousands of nanoseconds per day. Time, a difference
Yeah.
in the rate that time passes at the orbit of a GPS satellite and on the ground.
And we have to accommodate for that
You have to
when we
accommodate for
deal
that,
with
otherwise
GPS.
it doesn't work.
Yeah.
There's tens of thousands of nanoseconds per day, even around the Earth. So the question of black hole really is, as you said before, if I could keep the mass of the Earth the same, but shrink it down to the size of a pea, then how does that distortion change as I go closer and closer to this immensely massive pea thing? Then how does this is the effect that time keeps going more and more slowly from the perspective of someone outside until you see it stop on the horizon, which, as we said, for the Earth is around a centimetre, just a little bit less. So it's kind of not. In some ways, this behaviour of time is not unique to a black hole. It's just that in the black hole, it becomes extreme because the thing is completely collapsed.
So we have passed through the event horizon, we have been spaghettified, we have hit the end of time.
Yeah.
This is a question I think I know the answer to, but I think it leads us into our next section. The question is, can we ever get back out?
So the answer is, according to Einstein's theory, no, because you've gone to the end of time, right? And there's no way. Basically, Einstein would say it's all over. You've got ripped to bits. Everything has got ripped to bits. You've gone to this infinitely distorted space and time, and it's just done.
What would Stephen Hawking say?
Well, Stephen Hawking initially, in the 1970s, well, we should say, what did Stephen Hawking discover in the 1970s? So in his works, he discovered that black holes ain't so bad. So we've said nothing comes out of a black hole. Everything that goes in goes to the singularity, it's gone forever, because the black hole lives forever. Now, Stephen Hawking calculated that if you do some essentially quantum mechanics, right? So around the horizon of the black hole, so you think about what happens. What does a black hole do? A way of thinking about this is that in quantum mechanics, which means in reality, in nature, empty space isn't empty. There's a rich structure. So the vacuum of space has a structure. And the black hole, you might say, well, this strange behaviour of space and time, it must do something. And it does. It disrupts that structure. And the result is that particle photons, essentially, but what's called Hawking radiation, is emitted from the black hole. So the result, and there are different ways of thinking about what's happening. There's the very precise way. Stephen Hawking gave an analogy in his paper, and he said it's just an analogy, and people get very worked up online when we talk about his analogy, but Stephen did write it down, right? So a way to picture the quantum vacuum is that you can imagine particles coming in and out of existence all the time in the vacuum. So in accord with the uncertainty principle, they come in and out and in and out like that. You can kind of picture it like that. I emphasize it's not supposed to be a technical description, but you can picture. So you can picture these in the vicinity of the horizon. You can picture that this structure gets disrupted. You could have the situation where one of these particles is on the inside and one is on the outside. And then we know what's happening to the one on the inside. It's going to the singularity because we said the river of space is going fast in there, or whatever, whichever way you want to think about it. So the other one is basically made real and escapes. So that's a picture that Stephen himself gave. But the upshot is very accurate. The point is that this particle has been shaken out of the vacuum, but it's now a real particle when viewed from the outside, and it goes away. So that what is that? What particle's been emitted? It's a temperature. It's glowing, and so that means it's losing energy, and so that means it has a lifetime. So over time, and these are enormous times, far greater than the current age of the universe for any black hole that we know of in the universe, because we don't know of tiny ones. So all the ones we know of, the immense times, in excess of 10 to the power 100 years for these supermassive ones, right? Ridiculous times. But ultimately, they have a lifetime. And that means one day it will be gone. and space will be all nice and normal again, right? All you will have left will be the Hawking radiation that's been emitted over these eons of time.
Okay, I think something's missing.
Yes. I agree with you. Something's missing in my understanding as well, and everybody else's.
Here's what I think is missing from mine right now.
Yeah.
So all of this matter has, including us, passed through the event horizon, ended up in the singularity. It is something in there.
Yeah.
At the end of time.
So yeah, and it would increase the mass of the black hole, and the black hole would grow.
Right.
Because you've gone in.
And also, I think that I know that every law that we have about the universe says that information is conserved.
Yeah.
If a black hole will one day end up as nothing, the normal vacuum of space, what happened to you and me? What happened to all of that stuff?
I mean, this is the central question. So Stephen's initial calculation in 1974 was that this radiation, the Hawking radiation, is informationless. It's information-free. So it's not gone away. It's not disappeared, the black hole. It's turned into the radiation, right? But his calculation said there's no information in that. It's what's called thermal, purely thermal. Not surprising if you think about it, because it's been kind of shaken out of the vacuum of space. So it's certainly, you would think, got nothing to do with the stuff that falls in. This is something to do with the horizon. It's not anything to do with the singularity, this stuff. So out it comes, and the calculation is very clear. So that would suggest, as you said, that the information, any record of anything that fell in, will have been erased. The energy will be the same, right? The energy is conserved. The black hole hasn't vanished, it's turned into radiation, but the radiation contains no trace of anything that fell in. That is weird, as you said, because if you think, let's imagine, you might say, well, what's the difference? What if I get this piece of paper and set fire to it? It goes, and there's just stuff, ashes and radiation. Yes, but in principle, then if you could just measure everything, which you can't, but if you could, then you could reconstruct the information on the page. Right. And you can see why, because it's got something. What's happening when you burn it is chemical reactions and there's oxidation, whatever it is, but you can trace everything back. So you can say all the atoms and things are still around, and there it is. In a black hole, you can't. So it wasn't surprising. What was surprising is that it appears there is a calculation that tells you that black holes erase everything. And as you said, the laws of nature are quite clear on this. That information does not get destroyed in the universe. It gets scrambled so you can never reconstruct it, but it doesn't get destroyed. So that's what bothered everybody for a very long time.
What happened? What's the end of the story?
So what happens?
Answer the question?
So the end of the story, we're not at the end of the story yet, but in 2019, a series of papers were published. One of the papers was by Jeff Pennington, and the other one was by another group of authors. But those papers suggest that Stephen missed a bit in the calculation. Very subtle. You could have never seen it. Yeah, I mean, that's why it took 50 years, right, to see what he'd missed. But it turns out that the radiation is not information free. At the end of the process, then all the information about everything that fell in is imprinted in the radiation, as you would normally expect. But then it becomes interesting, because you say, well, okay, so there's a calculation, there's mathematics that was done. But you say, well, what's the picture then? What happened? Because I understand if I take this and throw it into the black hole, it's gone across the horizon, it's gone to the singularity. It's definitely true that nothing comes out of the black hole, but so how is this information about this thing getting imprinted in the radiation? And it turns out that it's not just so. Initially, quite a few people thought, well, it must be just right at the end when it's all quantum gravity and all this stuff. So the thing's just about to disappear back into the universe, and it's getting hotter and hotter, by the way, as it gets smaller and smaller. So there's more and more, getting more and more violent, and something weird happens, and everything comes out. But it was known for a long time. It was worked by a great physicist called Don Page. The problem about this, about the information and the structure of space, these problems occur about halfway through the black hole's life. So it's called the Page time. So the problems with the information structure of this thing occur way before you should be thinking about quantum gravity and a load of weird stuff. So there was a big challenge to physics. It's like we should be able to calculate stuff when the black hole is halfway through its life. There's nothing weird at the horizon, but yet something weird appears to be happening. The picture of the thing is breaking down. And so then we could skip, if you want, to the. So what is the picture of this? And I should emphasise the health warning. This is ongoing research, and there is no agreed upon picture. And there's some other subtleties we'll talk about in a minute. But a picture of what's happening is this is related to it's related to something called the holographic principle at some level, we think. And another discovery that was made in the 70s, which is quite interesting. By quite, I'm using it in the American sense, it's very interesting, is that, so Jacob Bekenstein,
Safer ways to
one
get
of the
your
pioneers along with Stephen Hawking, calculated what's called the entropy of a black hole. So this thing at the temperature, Stephen calculated the temperature, that is inscribed on his gravestone in Westminster Abbey, his equation for the temperature of a black hole. So it's a huge, fundamental discovery. Temperature is now, we understand it now. We didn't, when we first introduced the concept, we didn't know about atoms and molecules. Then we did, and we realised that temperature is about how fast the component parts jiggle around of a thing, right? So in this water here, you heat it up, the molecules are jiggling around faster, that's what temperature is. This thing, a black hole, think about what this is.
Whatever works for
I
you.
said the description of it is just space and time. That's all it is. It's geometry.
How about Johnny Mercer?
So immediately we've got the
I kind of wonder
temperature
if
of
this one is supposed to be
a
a joke.
geometry, not a temperature of
anyone
a
know?
thing made of stuff, but just a temperature of space, right? So that's kind of interesting.
Sounds
And
good.
then Bekenstein calculates that this thing has an entropy, which implies that it hides information from us. There's a structure, there's information in there. The entropy turns out to be equal
We
to,
almost done?
equal to the surface area of the event horizon in what's called square Planck lengths. So this is a remarkable idea, that you can think of the horizon. And I said, remember, it's not really there from our perspective. I said we could be falling through it and I wouldn't notice anything. According to Einstein, in we go. But then you look at it from the outside and it looks like there's information encoded on the horizon in pixels that are 1 Planck length in size. So what does that mean? That information's encoded in space somehow, on the surface? And also, by the way, it's weird, isn't it? If I said how much information is contained in this room, you would say, well, it's to do with the volume of the room, right? It's for the library, it's how many books can I fit in the library. This is saying no, at a fundamental level, the amount of information in this room is determined by the surface area of the room, not the volume. So this is almost as if nature has said you can paper the outside of the library with the pages of the book, but it's almost like there is no interior to this thing. So you start to get these hints that there's something very strange going on. What is happening here? So we've got this picture now, which was in the 1970s, of this thing that has a temperature and an entropy, which are calculated. And so that kind of is suggestive of substructure, but structure of space and time. What do we mean by that? So nobody knows. Nobody knew that, right? So then, so there's another thing that comes, another property that then comes, which is why I was careful about us falling in. And I kept saying, from our perspective, nothing happened. So you got this Hawking radiation. It's coming from the disruption of the vacuum in one picture. So it's all there, and it's coming away, and it's climbing away from this black hole, it's losing energy, and so it's very low temperature by the time you fall away from this thing. As you go in towards the horizon, if you lower the thermometer down far away, so our friends are in space, you've got the thermometer, they lower it down. The idea is no temperature at all.
From
Right? You don't see anything, you don't feel anything, you don't measure any Hawking radiation. You just go in because you're in free fall. So from your perspective, nothing's happening. From the outside, you've got this high temperature. So from the outside, a description of what happens to us is different. The description of what happens to us is that we get vaporized. We never get spaghettified. As I said, the other thing is we never
Yeah.
go in, right? So what happens to us? We get vaporized before we cross the horizon, and all our ashes and all the stuff comes out, and you could collect it, and you could say, well, that's fine, great. It's just like burning a piece of paper. But Einstein's theory is absolutely clear that from our perspective, we go in, we get spaghettified. So from our perspective, our demise, the description of our demise is spaghettification.
Yep.
From the exterior perspective, the description of our demise is incineration, right? So which one is it? So you say, well, come on, you either get incinerated or spaghettified. Which one? The modern view, at some level, that is much debated, goes all the way back to work by Leonard Susskind and Gerard 't Hooft and some others. It's called black hole complementarity. And the idea is that both pictures are correct from different points of view. This is relativity in action, right? So the
Yeah.
idea is both pictures are correct. Now, so there is some, it's not as simple as that. And that even is not simple because there's other stuff going on here. But so you might say, well, okay, so I understand sort of this idea that the information, essentially you're saying that from the outside, things fall in and get scrambled up and are somehow stored close to the horizon. And you can obviously imagine these bits of information coming off as the Hawking radiation. Nothing really goes in. And so it's fine. I understand how that stuff got out. But then the question is, what happens? What's the description of that from our perspective going in then? Because we definitely went in, right? So we've gone in from our point of view. What happens? What's the other description?
Are there two of us?
No, that's a great question. So you might say, well, we get copied then. So there's a copy of us, mate. It's like Leonard Susskind calls it a quantum Xerox machine, I think. So he says, is it a quantum Xerox thing? Do we get copied? So, but there's a very fundamental theorem in quantum mechanics called the no-cloning theorem, which says you can't copy a quantum state. You can't copy the information. And this is fundamental. So this is a problem in quantum computing when you're trying to, it's another whole other discussion. So it's not copied. So what's the description? So this is where we get speculative and we're trying to understand what the mathematics is saying. One description of our perspective is, we go to the singularity, we get all scrambled up. And then it looks like the interior of the black hole is in some sense the same place as the exterior. You could almost picture wormholes opening up from the interior of the black hole to the exterior. And very naively, you imagine our bits of information going through the wormholes and coming out again. So we end up outside. The information ends up outside in the Hawking radiation. How it gets there, is it really wormholes that are connecting the interior? Is that what's happening? There is an idea that's been around for a long time. Again, EPR, which is Einstein-Rosen equals Einstein-Podolsky and Rosen. Okay. So Einstein-Podolsky and Rosen, very famous paper, was about quantum entanglement. In the 30s, they wrote this paper, and they were very concerned about if you have these quantum systems that are so-called entangled systems, then you can make a measurement on this thing over here, and instantly this one, which might be a light year away, will have to reconfigure itself. The classic example is a quantum coin. So you can have a quantum coin in a quantum state, which can be heads, tails, plus tails, heads, let's say that, with a 1/√2, whatever. So if it's in that state, then it means that's a full description of the state, heads, tails, plus tails, heads. It means that if you separate these quantum coins, there could be an electron, right? You separate the quantum coins, to a large distance, then it's still the case that this thing is in this what's called a superposition of heads and tails. Then you make a measurement of it, you make an observation, whatever that you want to describe it. And if that one comes up heads, then you know this one is tails, even though before you did anything to this, they were both in this rather this entangled state, right? So that bothered everybody. Einstein, Podolsky, and Rosen, and they said maybe there's something else going on and whatever. But we think that's the way the world is now. Einstein-Rosen is the paper that Einstein and Rosen wrote, noticing that the Schwarzschild description of a black hole has a wormhole in it. So it's a wormhole. So Einstein-Rosen is a wormhole, EPR is quantum entanglement. So there's been this idea that they're the same picture of this thing. So you can picture quantum entanglement somehow.
As a wormhole between the two things?
Linking, yeah. So this was an idea from a long time ago. And so the picture of a black hole is kind of similar to that, in that we're developing this picture where the interior of the black hole, when viewed from one perspective, is the exterior of the black hole when viewed from another perspective. And so what you're getting there, we think, and again, even as I say this, there are papers being written saying different things. It's really cutting edge stuff. But I think what everybody agrees on, pretty much, is that you're seeing something called the holographic principle at work here. So it's a dual description of nature. So there's a very famous paper by Maldacena called the ADS-CFT conjecture. And I think I'm right in saying it's the most cited paper in all of theoretical physics. It was a very particular model of quantum mechanics on a surface. That's what CFT, conformal field theory, it means. It's quantum mechanics on a surface. And a precise proof that there's a dual description. This quantum theory describes an interior geometry of space, which was not there in the surface theory. And the space is called an ADS space, anti de Sitter space, or whatever. But it's a perfect proof that there's a one-to-one description between these two things. And I think it's fair to say that the black holes, these strange apparent paradoxes, are telling us that such a thing, our universe, can be described in such a way. So there are different ways of describing the same physics. And they're radically different ways. Ultimately, the thing is, it shouldn't be so problematic in that in both descriptions the information comes out. But the way it came out is radically different depending on your point of view. And so I think most people would say we're seeing glimpses of some kind of holographic. They're called holographic, by the way, because if you think of what does it mean to have a complete description of a higher dimensional thing? So let's be very concrete. This room. So let's say that this principle is correct, and many people think it is, by the way, for this room. So we have a surface surrounding the room, the walls, let's say, and there's a theory that lives just there, and it describes fully everything that's in the room. In